our final year project called Introducing Task Clustering to Distributed Workflow Management Systems. In order to understand the project well, let's go through some of the terminologies first. Our project evolves around scientific workflows. Scientific workflows are organized structures that contains a set of computational tasks and data dependencies between these tasks. Scientific workflows are organized as directed acyclic graphs, commonly known as DAGs. Nodes of the DAGs represent the computational tasks and edges represent data dependencies between these tasks. When we execute these jobs in high-performance computing environments, we have to wait in a queue because there is a high competition for resources. The time difference between when we submit the job to the system, and when it actually starts its execution, is called queue delay. To address this problem of queue delay, a common technique called task clustering is used. Under task clustering, several tasks are clustered together and input them as a single job to the high-performance computing system, so that we can reduce the queue delay and other overheads, like communication overhead between tasks. In our research, we focus on the following two main problems. Currently, there are two types of workflow management systems called centralized workflow management systems and distributed workflow management systems. Centralized workflow management systems are quite mature, and distributed workflow management systems have been emerged recently. These distributed workflow management systems currently do not have a technique to address the problem of queue delay. Further, existing task clustering techniques do not consider resource requirements when clustering. This leads to clustering tasks with large gaps of resource requirements, causing a large wastage of resources. Let's look at this resource imbalance problem we introduced in our research. It shows that conventional clustering reduces the makespan, which is the total time required to execute the whole workflow, but it causes considerable resource wastage. But, if you consider the new clustering approach we present, you can see that we can have a makespan around the same makespan, while having a much lower resource wastage. As a solution to this problem, we introduce a new task clustering algorithm called resource-aware clustering algorithm. In the heart of this algorithm, we use a metric called resource-aware clustering coefficient, which takes both the time requirements and resource requirements of these tasks. Then, it tries to allocate these tasks in an optimal way so that both makespan and resource wastage of these scientific workflows are minimized. Using this resource-aware clustering algorithm, we introduce a new distributed workflow management system called SwarmFirm. It accepts existing workflows and clusters these workflows using SwarmFirmer, which is the clustering component of this system. With this, SwarmFirm introduces tasks clustering to distributed workflow management systems. Further, it provides an extensible interface that can support any clustering algorithm so that anybody who uses or introduces a new clustering algorithm can integrate it into SwarmFirm and use it without modifying the core code base. It also provides dynamic workflow support, in which the workflows can be dynamically changed at the runtime. Finally, we have a DAX to YAML converter and workflow generator that can be used for simulation purposes. SwarmFirm is available as a pip package that can be downloaded and used by anybody. To obtain more details on our algorithm and our SwarmFirm distributed workflow management system, you can refer to the following 3 publications. Thank you.